Thanks for checking out the video. I'm going to be going through the Bode plot review, go through the notes a little bit, and hopefully make things more clear than if you just read through them by yourself. So in terms of the Bode plot review, I think the best way to look at it is to break it into three sections. First, let's talk about what is a transfer function. So let's very quick review. Obviously, this won't be a complete introduction, just a little review, assuming you've seen it before. And then we'll talk about what is a Bode plot and how do you draw one given a transfer function. And then once we establish that, we'll go to the third point, which is how do you now find the transfer function of a circuit. So the first point is, what is a transfer function? A transfer function is used to find how a system behaves to a certain input. So if x of s is our input, this is all in the Laplace domain. I have a note over here saying that, yeah, you actually do have to learn this. This is going to come back again and again. So this is in the Laplace domain. We're showing it in x of s. It goes through some system, which we're going to label h of s. And then you get an output, which is y of s. And in the Laplace domain, hopefully you learned in, I guess, your previous courses, that you get the input multiplied by the output, and your input multiplied by the transfer function of the system, and you get your output y of s. Now, with h of s, we can determine the system response to any input. So this is if you have, for example, a sinusoidal input, a step response, a square wave, whatever you like, you can figure it out. And again, these can all be expressed in time domain as well, where h of t would be, you would have to do a convolution to get the output. But in the frequency domain, you can just multiply them. If we now replace s by j omega, which is one thing that you do if you're interested in dealing with only sinusoids, you can get a transfer function, basically h of j omega. And when that's useful is it's used to predict the system behavior to sinusoidal inputs. Now you might ask yourself, well, we don't always have sinusoidal inputs, so why would I even think about that? That's not general enough. But then one other thing, I guess that's down here, that question I just asked. And the answer is that any signal can be written as a sum of sinusoids. Okay, so you'll learn that in your signal processing course, but for now, take my word for it that you can write any signal as a sum of sinusoids. So then it comes down to, now we make things a little bit simpler. We have a sinusoid input at a specific frequency. It goes through our transfer function h of j omega, and at the output, what you always get is another sinusoid at the same frequency, but with some amplitude modification and some phase modification, as I'm showing here. So what the transfer function will capture is what happens to the amplitude and phase of the input. So the main argument here is that this can be very useful, and the main point is that the reason it's very useful is because you can write any signal as a sum of sinusoids. So now let's go about the point of, okay, now you're given an h of j omega, which again in this course in 231 you specifically will be, and you'll be asked to draw a Bode plot. Now I'm going to cover some of the rules and some of the points, and as you get more advanced it can get more complicated, but this should definitely be enough to get you started. So since h of j omega affects amplitude and phase, a Bode plot is actually two plots. There's a plot of the amplitude and a plot of the phase. So let's start by looking at a transfer function h of s, and then talk about a few definitions, a few terminologies that you need to know, and then we'll convert it to basically put s equals j omega, and then look at that further. So if you have h of s, what we say is that anytime any frequency, any value of s for which the numerator is 0, we call that a 0, and any value for which the denominator is, for any value of s which the denominator is a 0, we call that a pole. If you have a term, so for example, let's look at this for a second, 1 plus s over omega z1. If s equals minus omega z1, then the numerator would be a 0. The fact that it's a minus means that you have a 0 in the left half plane. We won't deal with that right now. That should have been something that you either saw or hopefully will see in some control courses or circuit theory courses. But for now, let's just stick with the definition that when you have omega z1, you have a 0, omega z2, another 0, all the way up to omega zm. So those are normal zeros. When the denominator becomes a 0, for example, at omega p1, as we said, it would be minus omega p1, but we're going to not worry about that right now. Same thing for omega p2 and so on. If you have an s in the numerator, you have 1 0 at the origin. That's what we call it. If you had, for example, s squared, you'd have 2 zeros at the origin. If you had s cubed, 3 zeros at the origin, and so on. At the bottom, if you have a s, you have a pole at the origin. If you had s squared, you'd have 2 poles, etc. Now, obviously, I'm aware that if you put s cubed over s squared, they would cancel. The s squared would go away, and you would just end up with a 0 at the origin. I just put this here so that we can get the definition out of what they're called. And again, I've written that down here, what I just said about them canceling out. So what we said is, okay, we found h of s, or it was given to us. The first step is to put s equals j omega, which means we're going to deal with sinusoidal inputs. Then we can go ahead and try and draw a Bode plot. So all I've done in this expression, it's the exact same expression, except I have replaced s with j omega everywhere. So again, if you had a j omega in the numerator in this form, you'd have a 0 at the origin, j omega denominator, pole at the origin. Now you can see here that when your numerator is 1 plus j is what we call a 0. So if I put omega z1 here, where omega z1 would cancel, then I would get 1 plus j. So I would have a 0 at omega z1. Similarly, a 0 at omega z2, and so on. So if this seems a little bit confusing right now, don't worry. One of the easiest ways to learn how to draw Bode plots is by going through a few examples, which we'll do now. First, let's establish what are the main plots what is a Bode plot look like, and then we'll go through an example. So like I said, it's trying to capture the effect of this transfer function on the input. And that transfer function affects the amplitude of the sinusoid and the phase of the sinusoid. So we're going to draw both. On the x-axis of a Bode plot is the frequency. So essentially, basically, I would plot frequency on the x-axis. Now, one important thing is that this is plotted in semi-log x, which means that points that are equally spaced on your sheet, like when you're plotting it, are separated by a factor of 10. So for example, if I did frequency 1, this would be frequency 10, 100, and so on. And you can see these are equally spaced out, but they're spaced out in frequency by a factor of 10. This is to enable us to draw a large range of frequency responses on a small sheet of paper. Otherwise, and it also gives you more insight as to what's happening through a very large range of frequency responses. If we did it in linear scale, basically the majority of the plot would be the large frequencies, and there would be a very little portion that covers small frequencies, so we wouldn't be able to see things as clearly. Okay, now for the amplitude plot, we're going to plot it in dBs, which means that we're going to take the magnitude and then the log of the transfer function. When we're dealing with voltages, so meaning we put a voltage at the input of the system, and we want to see what happens to the output voltage, we do 20 times log base 10 of the transfer function. So that's the y-axis is in dBs, 20 times log of h of j omega when we're dealing with voltages. For the other plot, the phase plot, we just plot the phase of the complex number of the transfer function. Again, we'll go through an example to make that more clear. Okay, and we usually plot the amplitude and phase on top of each other, like I'm doing here, so that they can easily line them up and see what happens to the phase and amplitude at the same points. Okay, so first I'll talk a little bit, again, this will get more clear when we get to drawing one. So a note here, don't panic, right? The rules are going to seem overwhelming, but very quickly you'll get it when we go through the example. So we want to plot 20 log of h of j omega and the phase of h of j omega. Now, the rules that I'm going to lay out here, which again should be, hopefully you have at least seen before, is to enable you to draw Bode plots quickly, right? So a few approximations of what happens when at the frequency of a pole or a 0 to your plot, and then you can obviously draw a more precise one if you had more time. So when you hit a 0, a normal 0, so at the frequency of a 0, that's what I mean when I say you hit a 0. So basically that would be any of these, omega z1, omega z2, all the way up to omega zm. What happens is that the slope of your magnitude plot changes by plus 20 dB per decade. So whatever the slope was, it increases by 20 dB per decade at the omega, where again we said we would get 1 plus j in that term. So in this case, if I had a numerator that was this, 1 plus j omega over 10, at omega 10, so the frequency 10 radians per second, is when my slope would change by plus 20 dB per decade. Now for a 0, the total phase change is plus 90 degrees, which means that basically the entire effect of the 0 will be that it will change the phase of the transfer function by 90 degrees, and the phase change starts 1 decade before the 0 location until 1 decade after the 0 frequency. So again, in an example, this will become clear, and the slope would be 45 degrees per decade, obviously, if you're going to start 1 decade before and 1 decade after and get a total of 90. If you had a pole, everything is the same, except that the slope changes by minus 20 dB per decade, and the phase changes by 90 degrees over minus 90 degrees over 2 decades, whereas it was plus 90 for the other case. Okay. If you have a pole or 0 at the origin, that just determines the starting slope of your Bode plot, because we never go down to 0 frequency because we're plotting it on semi-log scale. We'll never get to 0. So all this does is just determine what is the starting slope of your plot. So if you had 1 0 at the origin, for example, you would start at plus 20 dB per decade. If you had 1 pole at the origin, you would start at minus 20 dB per decade. 2 poles at the origin, minus 40 dB, and so on. And same thing, the starting phase would be minus 90 for 1 pole at the origin, minus 180 for 2 poles at the origin, and so on. Okay, the only final thing to point out before we do an example and hopefully clarify everything is that we need to pick a good starting frequency. And what that means is, well, we want the space on our plot to be utilized as efficiently as possible. So we want to pick a frequency that is obviously much less than any first pole or 0 frequency, so that we can see the entire effect. And then we get a reference at that point and put it on our plot. So let's do an example and it will become clear. Let's say that we have a very simple transfer function, which is shown over here, h of j omega. So h of j omega, in this simple example, we can see that we have 1 pole at omega equals omega naught. So if we have 1 over 1 plus j omega over omega naught, that we can see that we have 1 pole at omega naught. So let's now try and draw the Bode plot. So what we said is we would start at a frequency that's much less than our any pole or 0. So I have a pole at omega naught, so I'm going to go a few decades below it. I'm going to start at 0.001 omega naught. And my slope is 0 dB per decade to start with, because I don't have any poles or zeros at the origin, which would have been here. And then when I hit omega naught, my slope changes by minus 20 dB per decade, which you can see here. So now I am going down at minus 20 dB per decade. Okay. And that's it. There's only 1 pole, so that's the only thing that happens to the magnitude response. That's easy. Let's look at the phase. I have no poles or zeros at the origin, so my starting phase would be 0 degrees. And then 1 decade before the frequency of my first pole, which is 0.1 omega naught, until 1 decade after the frequency of my first pole, which is 10 omega naught, I start dropping at minus 45 degrees per decade. And so I end up at minus 90 degrees after that. So that's it. You've drawn your Bode plot. The only thing that's missing is we need that reference point. Remember, I told you that every time you hit a pole, the slope changes by minus 20 dB per decade. But we don't actually know what this point is. I mean, I've labeled it as 0 dB because I've calculated the transfer function and seen that it's 0 dB at that point. So you would have to do this and see what that value is. So if that's confusing you, I realize I didn't write it. Actually, I did write it. Sorry. Let's look at it over here. So at low frequency, if you plug in omega equals, let's say 0.001 omega naught and solve for this transfer function, you actually you get that it's 0 dB. Same thing for the phase, you get that it's 0 degrees. So you know that's your reference point. And then from then on, now you can calculate what the value would be at any point in the plot. Okay, let's try a more complicated example. Actually, before I go to that, I want to point one thing out. You can see that obviously this transfer function is in a specific format, right? So that they're sort of isolated. The zeros are isolated from each other and isolated from the poles. So this is something that you're going to get used to when when we go to the third step, which is to find the transfer function given the circuit, we can actually take a look at this and see how we would rearrange it to get it to be in this format. So don't worry if you don't know that right now. Hopefully that will become more clear a little bit later. Okay, so let's look at another example. Here, I'm trying to now do something a little bit fancier, right? So, okay, let's look at it. First thing we see is we have a 0 at omega equals 1, which is shown over here. We see that we have a pole, we see that we have a pole at j omega, at the origin, pole at the origin. So that means that determines our starting slope is minus 20 dB per decade, and our starting phase is at minus 90 degrees. We see that we have a pole at omega equals 100, and another pole at omega equals 10,000. Okay, so let's see, when is the first pole that anything really happens? We see that, okay, the pole is 0. So we see that there's a 0 at omega equals 1 radians per second. So we want our plot to start below that. So I've chosen to start my plot over here, which would be 0.1 radians per second. It's a good point. Okay, we have a pole at the origin, so our starting slope is minus 20 dB per decade, covered. At omega equals 1, we hit a 0, which means our slope changes by plus 20 dB per decade. It was going down at minus 20, changes by plus 20, so it becomes 0 dB per decade. At omega equals 100, we hit another pole, so our slope changes by minus 20 dB per decade, which is this slope over here. And then at omega equals 10,000, our slope changes by another 20 dB, so my slope here would actually be minus 40 dB per decade. Wow, that is huge. Okay, so that's not too bad. Now let's take a look and see what the phase response looks like. So again, we have a pole at the origin, so our starting phase is one pole at the origin, minus 90. My 0 was at omega equals 1. And I know that at 1 decade before that, until 1 decade after that, my phase is changing by plus 45 degrees per decade. So I go from minus 90 to 0 over those decades. My next pole is at 100, which means that a decade before it, which would be at 10 radians per second, my slope is minus 40 dB per decade for 1 decade before until 1 decade after. So if here I've come back to minus 90 degrees. Here again at 1000, I see that 1 decade before my other pole, and so my slope is going to be minus 45 from 1000 to 100,000. So again, you can see that over here, and then it flattens out at minus 180 degrees. So now we've drawn a Bode plot for a more complicated case based on the quick rules that I explained. Before we go on to looking at how to find the transfer function of a circuit and then draw the Bode plot, let's talk about the rules that I told you and kind of understand where they come from. Because it's easy to say, okay, when there's a pole, the slope changes by minus 20 dB per decade, but let's see how that comes about. Okay, so let's look over here. Let's say we have a simple transfer function. Hopefully by now this is obvious that this has a pole at omega p. Take 20 log of that. This should actually have the absolute values here. Take 20 log of that, and there you go. Looks like that. So if omega is much, much smaller than omega p, so that means that this term would be very close to 0. So you just get minus 20 log of 1. Again, remember, the reason for the minus is that basically it's just yeah, I think that's obvious. The log becomes minus when I got rid of the 1 over. So you get minus 20 log of 1, you get 0 dB. So the pole has no effect. It's not really doing anything. If omega is much, much bigger than omega p, then this one term really doesn't matter as much when you find the magnitude. And the main thing is minus 20 log of omega over omega p. Now let's see. If I put 10 times omega p here, I would get minus 20 log of 10, which is minus 20 dB. If I put 100 omega p, I would get 40 dB. So you can see that I went up by a decade and my magnitude went down by minus 20 dB. That's where the minus 20 dB per decade slope comes from. You can do the exact same thing for a 0 and figure it out based on that. So for the phase, let's recall the phase of a complex number is the phase of the numerator minus the phase of the denominator. So to find the phase of this expression, it's the phase of the numerator minus the phase of the denominator, and they're obviously complex numbers. If omega is much less than omega p, this term goes to 0, so you just get 1 over 1 plus 0. The phase of the numerator is 0, the phase of the denominator is 0, so you get 0 degrees. If omega is much bigger than omega p, then what happens is, again, your expression can be approximated as 1 over j omega p over omega, and then the phase would be 0 minus tan inverse omega over omega p. Let's plug in a few numbers. If I plug in something really small, like 0.1 WP, I get 5 degrees. At omega equals omega p, I get minus 45 degrees. And then as I go a decade above, you can see it's 84 degrees. We're approximating this as 90, but the total phase shift of a pole would be minus 90 degrees. So again, if I go up here, and these notes became really messy, really what these look like is something like that, and what it looks like is something like that, and then eventually hits minus 90. So it's just to say that the rules are a bit of an approximation, and you can see exactly what the values are based on that. I just put a note here because this is the amount of notes that I could print for you guys. If you go to our Facebook page, I also put a tiny URL here, so you don't have to type this whole thing. You can get the full note, so the remainder of this would be on there. Feel free to ask questions or leave comments if you have any feedback about the notes or the video. Okay, now we've come to the final point in this video, is that how to find the transfer function of a circuit. So for 231, you'll mainly deal with passives, which means resistors, capacitors, and maybe some inductors. If you go on to take future electronics courses, we'll get fancier, and the transistor transfer functions will also be incorporated. But for now, let's focus on the absolute basics, make sure you get these, and then we can make it obviously fancier later on. Two main circuits that you really have to learn in this course, if not have already learned them, is a low pass filter and a high pass filter. So a low pass filter will allow low frequencies through it, and we'll talk about what low means. And if you put really high frequencies, they won't make it through. High pass is the opposite. If you put low frequencies at the input, they won't show up at the output. But if you put high frequencies at the input, they will show up at the output. That's a high pass. Now, band pass is somewhere in between. It doesn't let through low frequencies or high frequencies. It just lets through frequencies within some range. Again, hopefully that's somewhat intuitive. Okay. The one thing I really like to do when I'm teaching anything is that, and I also liked it when I was a student, is that I want a systematic approach. An approach that if you follow every single time, you get the right answer, or you can do your analysis, complete your analysis. Whereas I really don't like it when every single question requires some amazing ingenuity or some massive intuition to be able to solve. So we're going to try and stick to systematic approaches as much as possible. And if there's ever some magical insight that you need, I'll try and let you know. So how do you find the transfer function and draw the Bode plot for the above circuits or other more complicated circuits with passives? The first thing is you replace all the components with their Laplace domain impedance. You write a transfer function, V out over V in, and you find H of S. Replace S with J omega, and then draw the Bode plot with the above rules. That's it. We're going to do two examples, low pass and high pass, go through them both completely, and hopefully it'll get you prepared for fancier circuits. So a resistor valued R is just, again, it's the R in the Laplace domain. If you have a capacitor, it's 1 over SC in the Laplace domain, the impedance. If you have an inductor L in the Laplace domain, it's SL. So those ones you should remember. Let's look at a low pass. So what I'm going to do is I'm going to replace the R with the R, obviously. I'm going to replace the capacitor with 1 over SC, and then I want to find V out over V in, which is defined as H of S, and then draw the Bode plot. So I'm going to use voltage division. So that's the impedance over here divided by the total impedance, the sum of the two. So 1 over SC divided by 1 over SC plus R times V in gives me V out. Now, if you look at this format, it doesn't look anything like the one we looked at on earlier, which would have been page 2 if you printed the notes out. So we're going to try and get it in that format. Let's multiply the numerator and denominator by SC, so it looks like this. Then let's try and get it to look like that format. So I'm just going to replace, I'm going to do S over 1 over RC, so that it would have been SRC, but now it's in that format. Now if you look at this, you see that you have a pole at 1 over RC. Okay? Did I mess that up? No, that's fine. Sorry, cut that out later. Okay. Then the next step, which was in our list, was to replace S equals J omega. Done. You get H of J omega, and then 1 over 1 plus J omega over 1 over RC. So again, this is, I've written that the pole is at 1 over RC. There are no basically there are no poles or zeros at the origin. Sorry, so we know that what is our starting slope? 0 dB per decade. Okay, so that means that we know our starting slope is 0 dB per decade. We're going to need a reference point at some point. We'll do that at the end. We want to start it well below our frequency of our pole, which is 1 over RC. I've labeled 0.1 over RC, and you can keep going, and 10 RC on this end. I know that when I hit the pole, my slope changes by minus 20 dB per decade, and that's it. And all we need is this reference point, which we'll calculate soon. Starting phase is 0 degrees because there's no poles or zeros at the origin. 1 decade before the frequency of my pole, which is 1 over RC, I start decreasing my phase by minus 45 degrees per decade until 1 decade after my pole. So that's these 2 points. You can see I started here, and I fell total of minus 90 degrees. Okay, now to replace this, to basically put our reference point in, we pick a low enough frequency. So I'm picking, let's say omega equals 0.01 over RC. So it's 100 times less than the frequency of my pole. Plug the numbers in. You'll get really fast at this. I mean, these ones don't even matter, but I just put it here just so you see it, because it'll just be 1 over 1. And you get 0 dB. So I put that here in my plot. Don't forget to do that. You don't want to lose any extra marks. Okay, so now I have labeled all the slopes on both plots. I've labeled the reference point. The Bode plot is complete. Okay, now why is this called a low pass? Okay, so at low frequencies, right, which is over here, basically frequencies below the frequency of the pole, so that's this whole region over here, the gain is 0 dB, which means 1 volt over volt. So whatever I put at the input, that exact same thing shows up at the output. So low frequencies, lower than my pole, all show up at the output. Higher frequencies than the pole, as shown here, become a negative number in dB. So for example, if you convert minus 40 dBs to volt per volt, you get 0.01. So that means that whatever I put at the input, only 1% shows up at the output, which means that high frequencies are going to get attenuated. They're going to become smaller. They're not going to make it through, but low frequencies are going to make it through. So that's when you know that it's a low pass filter. Let's do the exact same thing very quickly for high pass. Switch the capacitor and resistor. Let's do the same thing. Do a voltage division. So you get R over 1 over SC plus R times V in of S. Go ahead and rearrange. Again, you want to put it in the same format. So look, if I do it in that format, I get that I have a 0 at the origin, and I get that I have a pole at RC. Okay, that's not too bad. Step 3, S equals J omega, and let's go ahead and try and draw the Bode plot. First thing we know, when we have a 0 at the origin, our starting slope is minus 20 dB per decade. When we hit the frequency of our pole, the slope changes by minus 20 dB. So it was going at plus 20, changed by minus 20, becomes 0. Do the same thing for the phase. 1 decade before, we know that we start at plus 90 because we have a 0 at the origin. 1 decade before, we start to drop at minus 45 dB per decade until 1 decade after, as you can see here. And so that takes care of the phase. Now we need our reference point. Let's pick, again, 100 times less than the frequency of our pole. Plug the number in. Do the analysis. You get that it's minus 40 dB. So I put that reference point here of minus 40 dB. Now, why is this a high pass? Frequencies above the frequency of that pole, they go 0 dB. So whatever you put above that frequency, that exact same thing shows at the output. Things below that are negative dB, so they're getting attenuated. So lower frequencies are not making it through. All right. I hope that was a little bit helpful. If you guys have questions, you can post it on the Facebook page or the YouTube video. I'll try and answer them. If you also had any problems with this specific video, the audio or anything like that, or it was too fast, too slow, you can also give me feedback. I'd appreciate that. Thank you.